Okay, so today we're going to be talking about probability distributions, which is kind of like a big word, but I'm going to break it down a little bit later. We're not even going to talk about the word probability distribution itself throughout this class. However, it can be summarized by using figuring out game theory stuff, but this time we have variables. Ooh. All right, but first, before we get to the main event, we got to do the two-thirds game again. So if you remember, this was introduced like 2 classes ago. Everybody had to pick a number between 1 to 100, and who was closest to 2/3 the average wins, right? And I set up a Google form so that you can enter in your guesses into the Google form. Second. Oh, you guys won't see the number of responses if I scroll down any farther, but no number of responses.
Are we doing it again?
Yeah, we'll be doing it every week to see how it changes overall again and again, right? Because we've had 2 rounds of this previously, right? And the first round, we saw that the average was 33 because like people were saying 33 is probably going to be a round where people are guessing.
I already responded it, so you have to make. But I already responded it, so you have to make like a new form. Like I responded it last week.
If you responded to it, no, I made a new form for them all, I believe.
So who won?
This is a new form compared to the last one. So you should be allowed to submit again.
But this is I already responded.
If you already responded, then you probably responded at the end of last week.
Responded.
Yeah, I responded at the end of last week.
Yeah, if you respond at the end of last week, then you should have already like been responding. But otherwise, all right, we're doing the 2/3 the average game, and remember, everybody has to pick a number. Try to figure out which number is closest to 2/3 the average, and yeah. And remember, the last average last time for round 1, it was about like 33. 2/3 the average was 22, so our winning number was 21. But this time, it looks like last time, it looks like a lot of people guessed 21, right? Because people saw that 21 was the winning number. And so the average was suddenly 14, and 14 won. So maybe people are going to guess 14 this time. So then 2/3 of 14 would be like 10. So maybe 10 is the winning number. Maybe people are thinking even deeper than that. So maybe it would be 6, or maybe even 4. Maybe 3, or maybe 2, or maybe even 1. Maybe everybody's actually just saying 1 because we're already all at Nash equilibrium. All right, got 3 more responses. Ooh, drum roll. 4 more responses. We have now at 11 responses. I'm gonna figure out how many people responded to the last one. Yeah, this is the all of the sheets. So this is the first sheet, right? 15 people responded last time, so hopefully we should get.
Can we wait a bit?
Yeah, of course. I know people are probably still trying to respond right now, so we'll see. As I say that, somebody responded, which is why I went up to 12 responses. Oh boy, I wonder what people are guessing. Well, you can see all of the guesses in this one below. There's a couple of interesting ones. 2 people said 1, a couple of people said 5.
You shouldn't give it out because other people could tell the average.
No, this is last
This was
week.
the first one.
Oh.
I mean, the first one that we did, I did it in Zoom chat and I had to add up all of the numbers manually, which is kind of a pain, which is why I changed it up into this thing. However, we're okay. Now we have 13 responses.
How many times did we have to like fill out the form?
This has always been like a different form. You can tell it's a different form because of the color, because this first one's the green and next one's purple. You're gonna have one after that. It's gonna be blue. Okay. Has everybody who's wanted to play submitted some answer? All right. If you want to like submit something through the form, but you just haven't already, I'm gonna send the form again, And if you haven't done it, then just tell me in chat that you want to like submit something, and I'll wait for you. Otherwise, I'm going to move on. So, like, 15 seconds. Tell me in chat if you want to do more.
Maybe everybody is choosing one.
Could be.
I doubt it, or maybe it's everyone's choosing 100.
I'm going to stop the game once everybody picks one, because if once everybody picks one, it gets really boring because everybody's going to pick one. All right, I'm going to stop the share right now because I want to like give a see what the average is this time. Okay, that is notably higher than what it was. I thought it was going to be. I see that somebody sus responded. All right.
Wait, what did he choose? Crazy number 100?
No. Sus actually had, I don't know if that's a legitimate guess. It's probably legitimate. Let's see here. I'm trying to figure out who is the winner. Oh, that's actually very interesting. Okay. So our winner is Amanda. Amanda was the first one who submitted. Actually, she submitted yesterday and was like, wait, was she? Okay, I don't even remember, but. And the closest thing to 2/3 the average was the number 12. Now, what I think was interesting is that, so I was looking at these numbers before people were submitting today. Like people submitted last week because I had the thing out last week. And most of the people, they were submitting like 12, 6, 6, 5, 4, 1, 7. And the average was 6 and 2/3 the average was 4. But because so many people like came in later, somebody submitted 17, 9. Somebody submitted 99, which is kind of a little bit interesting.
That definitely changed it. That's like not fair.
99 definitely changed it, yeah. I mean, that's assuming like everybody picking one is assuming that everybody is trying to win, right? Some people aren't trying to win, they're just trying to like troll. So like 99 kind of makes sense in that perspective, right?
What if someone put like 10 million?
You can't pick a number bigger than 100. So that kind of limits the amount of trolling that you can do, but it still affected the average a significant amount because our average.
Could you put like 100.001?
No, no. It only goes up to 100.
You from adding 100, which I tried that.
You tried that? Oh, okay.
You can't put 100.
I should have done 99.9. Dang it.
You put 99 point and a bunch of other numbers. Like, can you put pi in the chat? Like pi in the form?
You can put any decimal. I mentioned before that I was surprised that people hadn't been doing that because, yeah, our average was 18.35 and 2/3 the average was 12.2. So our winner was Amanda. All right, good job.
I got 6.
Yeah, 6 would have been the average actually a little bit ago, but it's no longer the average, which is sad. But the guesses would have been really low. But I guess because we have somebody submitting 99, the average was pretty high. All right.
Wait, could you put in 0?
You cannot put in 0.
It's 1 to 100.
Okay. So something that might have confused you earlier is that if you remember, we saw in the lecture for the prisoner's dilemma, you saw the prisoner's dilemma as like the soapbox where you had -6. If both people confessed, they spent 6 years in jail. If both people didn't confess, they would spend 1 year in jail. If one person ran out the other, the person ran out the other would spend 0, and they would spend 10, right? However, if you did the evolution of trust simulation, if you remember that, instead, we had this situation, right? Where if you guys both cooperated, you both got 2 coins. If you guys both cheated, you both got 0 coins. And you cheat, they cooperate, then you get 3 coins and they lose 1 coin, right? And the evolution of trust still called this a prisoner's dilemma. So which of these actually is prisoner's dilemma, right? How can both of these be prisoner's dilemma. They're completely different. This one is full of negative numbers. This one is full of both positive and negative numbers. So you can't even make a comparison in that way, right? They have completely different values. This is like +3, +2, -1. This one averages out to a positive number, but this one averages out to negative because literally every single number in it is negative or 0, right? So what gives? Well, how come we can have all of these different types of prisoner's dilemma? So which is it? Which brings us, what?
Both?
Yeah, both are prisoner's dilemma, right? Which brings us to generalizing games. These are both valid prisoner's dilemmas. So what makes prisoner's dilemma the prisoner's dilemma? Can anybody tell me in chat maybe?
It's prisoner's dilemma.
I mean, yeah, but like you can be told this is prisoner's dilemma, right? But what exactly makes prisoner's dilemma, right?
There is negative numbers.
Well, this one has negative number. I can think of at least one example where prisoner's dilemma doesn't include negative numbers.
Because it is prisoner's dilemma.
I mean, yeah, but then how do people, who decided that both of these were prisoner's dilemma? I can come
there's like a choice between like I know I have something in my mind, but I can't explain it.
Right, so another prisoner's dilemma situation would be like, I don't know, 5, 5, 1, 7, 7, 1, and then 3, 3, right?
Yeah.
This is a prisoner's dilemma, but why is this a prisoner's
You
dilemma?
can both make choices.
I mean, they can both make choices.
Yes,
And confess.
They can both make choices, and I don't know. Can you tell me if this is prisoner's dilemma? Let's see here. What should I say here? Maybe 4, 3, 2, 1, 7, 6, 5, 5. Is this prisoner's dilemma?
Yes.
Well, actually, it isn't, right? Because it doesn't have the things that really make prisoner's dilemma. So I feel like one of the biggest things of prisoner's dilemma is that both players are motivated to confess, and both players' best strategies are to confess, right? If you look at both of these scenarios, it is always better to cheat versus not to cheat, right? Or confess versus not confess, right? That's what made both of these prisoner's dilemma. We've already analyzed this question to bits on day 1. So hopefully you remember that confess is always better than not confessing because it's always better to spend 6 versus 10, and it's always better to spend 0 versus 1, right? However, I don't know, this may be a little bit unfamiliar if you didn't do the evolution of trust simulation.
So always cheat is better?
Yeah, always cheat was something that was always with prisoner's dilemma, right? It was always going to be the best play for both players, right? If you remember here, or if you don't, probably don't remember because you might not remember if you didn't do the evolution of trust simulation, but it's +2, +3 is better than +2, right? Therefore, you would want to cheat if they cooperate. And 0 is better than -1, therefore you would want to cheat whenever they cheat, right? So in both of these situations, in all prisoner's dilemma, it's always going to be one option that is better than the other, right? What's another thing that's a characteristic of prisoner's dilemmas? Take 2 notes about this square and this square.
Well,
there are 8 numbers?
Well, confess and confess, they both are equal.
Well, that's very true.
Like
Yeah,
2,
that's
2 and 0, 0, 6, 6, 1, 1.
Yeah, that's also true. right? So one reason that you could say what I like drew like here, if you remember what I drew, is just a whole bunch of random numbers. That wasn't Prisoner's Dilemma because you see, whenever you guys both do the same thing, so if you guys both cooperate, right, you guys both get the same payouts, right? These are both either 0, 0 or +2, +2. And here we have either -6, -6 or -1, -1. These two are the same numbers no matter what. All right. So does anybody have anything else that makes Prisoner's Dilemma? There's some sort of deeper relationship I want to say about these two. And it's that, remember how we said that always confessing was always going to be the best option? Well, it's kind of like completely weird because if we look, we have a option that is 100% better than the option of both people confessing. That's getting -1, -1, right? That is 100% better than both players confessing. However, because of how this game is structured, both players will confess anyways, or both players will cheat anyways, even though cooperating is better for everybody overall. So I feel like another big part of the Prisoner's Dilemma is that both players are hurting themselves by confessing, even though that is the most logical and best option for both of them if they're playing one round.
So why not you just both don't confess?
Okay, so I mean, I explained this during week 1, but if you remember, if we both don't confess, right? You guys agree beforehand to both not confess, then what's stopping the other guy from confessing?
You get 0 years in prison rather than 1.
But if you know that they're going to confess, then you're going to pick something else that benefits you.
If you know that they're going to confess, if both players know that the other won't confess, then both players actively want to confess because, right, if you remember, in this -1, -1 situation, if player 1 confesses and player 2 doesn't confess, instead of spending 1 year in jail, they get to go completely free. Isn't that 100% better, right? If you know the other person is not going to confess, then you want to confess. If you know that the other person is going to confess, then you're going to confess.
But I meant that if you both decide to not confess, you know that he'll confess, so he can get like 0 years in prison. But then you pick something else that's better for you.
But there isn't anything else that's better for you, right? That's kind of the Prisoner's Dilemma part of it. It all leads to confess. That's the other thing that's better for you, which is actually worse for you, right? That's the whole dilemma part of the Prisoner's Dilemma. So I feel like the big things with Prisoner's Dilemma is that, firstly, we know that both players will want to be motivated to confess. Both players want to be motivated to cheat. Secondly, that option is always going to be completely worse than the option than another option on the board that's on like a completely opposite corner, right? But both players can't really exactly do that option or else they risk getting zeroed, right? So how can we apply this to numbers? How can we generalize the Prisoner's Dilemma? Instead of having numbers in the Prisoner's Dilemma, why don't we have variables or these numbers, or not these numbers, these letters. And these letters stand for things that could be any sort of number given some certain limitations. So I feel like we can agree that the general structure for all Prisoner's Dilemma games is that we have some sort of BB up here, right? That's exactly what Athena was saying about how this one is, what is it? These are both the same number whenever both players cooperate, and these are both the same number when both players don't cooperate. And also another thing that wasn't really pointed out, but I think was pretty much implied, was that if we have like 3, 1, then the other side would have to be 1, 3, right? If it was A, B, then you'd have to switch it around with the not cooperate versus cooperate, right? That was also sort of implied based on the structure. So we can write out a general structure like this. But also we have to limit how large or which cells are bigger than the other cells, right? Because both players are always motivated to not cooperate. So how can we do this? So firstly, if a player is motivated to not cooperate over cooperate, player 1 is motivated to do that, then the payoff for switching from B to A has to be really good. Therefore, our first relation is that A has to be greater than B. All right. Another thing is that we need to know that, what is it? Not cooperating is always better than cooperate whenever the opponent doesn't cooperate, right? So we're comparing D to C. And we know that C is always going to be better than D. Therefore, C is greater than D. Now, there are also a couple of other things here. And that is that you never want to, we know that in this A, B, AD, and DA situation that you always want to be, the person confessing is always going to get a bigger number. Therefore, we also know that A is greater than D. But I didn't really mention this because that's sort of implied with later statements. However, also we know that we're worse off. We're way worse off. Like if the opponent doesn't cooperate, then we know that we're going to be way worse off, right? Therefore, we know that B has to be better than D. And finally, we have the last thing, which is that doing the thing that's best for everybody personally is the worst for the group overall, right? We said that there was like something that's completely better in the opposite corner by cooperating, right? So therefore, our final relation is that B has to be better than C. Because as we said before, both players cooperating is 100% better than both players not cooperating. That was one of the core things of Prisoner's Dilemma. Therefore, we can describe Prisoner's Dilemma as a game with these like sort of variables instead of having actual numbers. This might make more sense if you take in like algebra class. I said that this class has, or this week's lecture class has a lot of math in it. This is only the tip of the iceberg of math, though, which is kind of unfortunate. But we can write the Prisoner's Dilemma in general as like some sort of form with this payoff matrix, and we know that it must follow these inequalities. And even sometimes you'll have AD is greater than 2B. So what this just means is that, AD should be less than 2B. 1 second. Sorry, it should be a less than symbol because I am stupid. But and the thing is, so a lot of the times, whenever both players don't cooperate, or whenever one player doesn't cooperate and the other player does cooperate, generally that has to be worse for the group overall than both players cooperating, which is why I have this sub here. But this is only true subtype. Sometimes you can have this option be equal to the other option, right? And overall, we can solve the Prisoner's Dilemma in general, right? Also, I'd like to point out how this follows both of the examples that we had before. So one example was the coin example. So in the first case, if both players cooperated, both players would get 2-2. If one player cooperated and the other failed, it would be, I think it was -1 and 3. So is it -1? Yeah, this is -1, 3, 3, -1, and then if both players didn't do anything, they both get 0, right? So let's see how this fits in. So this fits in the A, B, C, D stuff, and we thus know that B is equal to 2, that D is equal to -1, that A is equal to 3, and C is equal to 0. All right, let's see if they follow all of these relations that we said they had to have. A is greater than B. Check. A is greater than B. B is greater than D. B and D. Check. B is greater than D. B is greater than C. Check. 2 is bigger than 0. C is bigger than D. Check. 0 is bigger than -1. Right? So we know that this does work for this sort of example that we had before, right? If you remember the previous slide, that was the coins example right up here. You can also test out if all of those numbers work for this example that we had down here. However, I'm not going to go through all of the comparisons for the sake of time, because I feel like it's a little bit clear that this is a prisoner's dilemma by our definition. So we know, therefore, that we can generalize prisoner's dilemma as this sort of situation, right? So we might want to solve a game in general, right? And that would be pretty useful because then we know how it would play out overall. So this slide looks very similar to the last slide, but because we know that A is bigger than B, right? That was one of the conditions. And we know that C is bigger than D. We know that's always better to not cooperate. Right? We know it's always better to not cooperate for both players. Therefore, by dominated strategies, we know that cooperate is dominated by not cooperate in every single case. Therefore, we can generalize that prisoner's dilemma will always end up with both players not cooperating. And that's sort of how we set up prisoner's dilemma. So that kind of makes sense. However, what if we generalize other games? So does anybody remember any of the previous games that we covered?
Coin flip?
Yeah, there was a coin flip game, but that's not the next game that we're going to cover. This is like even farther back than coin flip.
Centipede game?
We did cover the centipede game. That's like not really in the form of prisoner's dilemma, but yeah, we did cover that game. Think way back to week 1.
Two-thirds game?
The what?
The two-thirds game?
Start. I'm trying to remember which one that was. Second.
Stag Hunt?
Yeah, Stag Hunt. That was the one I was looking for. Okay, Stag Hunt. So if you remember, we had a deal of Stag Hunt, and in Stag Hunt, we had these two hunters. One of them was hunting. You could either they could hunt a stag or they could hunt rabbits.
So isn't the dominant strategy just to hunt rabbit?
Well, we said that our strategy was there were two strategies. One was that both players hunt stag, and one was both players hunt rabbit, right? However, we all said there was a third strategy that was a mixed strategy.
I don't really know, because some people would want to hunt stag. Well, a lot of people, I guess. So you should hunt stag so you could get at least more.
You could view it as it's like, well, I don't want to go hungry, so I'm just going to pick rabbit.
Yeah.
Okay, so I just want to cover how we might generalize Stag Hunt, right? Whenever we had Stag Hunt on like the previous slides, it would always be both players get 5 here. One player gets 0, the other player gets 3. One player gets 3, the other player gets 0, and both get 3 here, right? So if you were to generalize Stag Hunt, we would get something like this. Right, so if both player hunts stag, then both player gets the stag payoff, so they both get SS. If one player hunts rabbit and the other hunts stag, the player who hunted stag will get 0, and the person who hunted rabbit will get R.
So this is basically a prisoner's dilemma.
No, if you remember from the prisoner's dilemma, it had well,
Stag hunt.
I think one of the core features of prisoner's dilemma is that it's better always to hunt rabbit or to go for this bottom option, right? However, if you look here, it's not always better to go the bottom option because getting stag is always better than hunting rabbit if the other person is hunting stag, right? So it's not so you wouldn't hunt stag over rabbit if the other person was hunting stag. You would go hunt stag with them. However, if you remember, there was also a mixed strategy with this, right? I don't remember the mixed in the big strategy like slideshow, we sort of covered how Stag Hunt also has a sort of third strategy, and that is to play Stag with a random chance and to play Rabbit with a random chance, right? I think it's pretty clear that even with this generalized form, we're going to keep the Stag-Stag equilibrium and the Rabbit-Rabbit equilibrium, right? Because no matter what, if we try changing from Stag to anything else, then it doesn't make sense because hunting Stag is better than hunting rabbits, right? And down here, you would never want to switch from hunting rabbit to Stag because hunting rabbit is getting food is better than not getting food because you know that the partner is not going to follow you, right? So I think the thing that we should be most concerned with here is the mixed strategy, right? So how do we solve that? So if you remember, we had those general algorithms to figure out how to solve mixed strategies. It required quite a bit of math to figure out the general probabilities, right? But what if we use that same math with these variables? We get lots of mixed, we get lots of math, which is lots of fun. But if you don't enjoy math, then you probably don't enjoy looking at all of these equations. However, these are the equations that will tell you exactly how Stag Hunt will work in general.
That doesn't look too bad.
I mean, if you take an algebra, it probably shouldn't look too bad, but just a lot of variables to deal with. But all right, so using the algorithm for, using the algorithm for mixed strategy, you want to make your opponents indifferent between picking Stag and picking Rabbit, right? Therefore, if they pick Stag, they have to have the same expected payoff as if they were picking Rabbit. So P times S plus 0 times P minus 1, that's the first slide, must be equivalent to P times R times 1 minus P times R, right? That is the second, what it's supposed to be equal to. Wow, the equation works. All right. If we know that, then we can simplify this. This 0 gets rid of everything here. This becomes PR plus 1 plus R minus PR. So this PR kind of cancels out, and all we're left is R. All we're left is R on this side. So we have P times S equals R. Therefore, our probability of choosing Stag is Rabbit over Stag. Whoa. And since both players sort of have the same options, or this is symmetry, right? This is sort of symmetric game. We see that it doesn't matter which player you are, in general, you're going to get the same results. We know that the other player will also pick Stag with probability R over S. And this is like a little bit counterintuitive because it sort of implies the better the rabbit payout, the more likely you should be picking Stag, which first glance said like doesn't make sense. But you're trying to make your opponent indifferent between choosing Stag and Rabbit. Therefore, to make Stag a lot more valuable, you choose Stag a lot more often. So by Nash equilibrium rules.
But you just pick Stag all the time. And then after a while, the opponent, after like 2 games or 3 games, the opponent will realize, well, he's just going to pick Stag. You're just going to pick Stag from now on.
Yeah. As if you're repeating play, but sometimes you're not just repeating play over and over again, right? But anyways. So this is kind of like pretty big because now we have just solved every single Stag Hunt game we could ever see. Now, if you see like any Stag Hunt game, you can always say, oh, there are 2 equilibrium that we see at S as Stag and Rabbit. And there's also a mixed equilibrium where we chose Stag R over S of the time, and we chose Rabbit 1 minus R over S of the time, right? So basically, we have solved every single possible Stag Hunt game there is, which is kind of like, wow, we just solved a lot of games. All right. Are there any questions about how the basic idea of how this math all works together? For the next couple of slides, we're just going to be focused on using this newfound knowledge to generalize games that we've already solved. All right. Moving on. There are a lot of other games that we covered, right? Pretty sure that somebody mentioned this before whenever I was asking for other games that we
Are
played.
we going to do for homework the same thing we did last time?
Yeah, we are actually, but I have to get the link up and I haven't put up the link yet. So just gotta wait for until the near the end of class where I'm gonna put it up. So we can also generalize matching pennies. And we kind of already knew that this game could be generalized because if you remember correctly from whenever I first explained this, when we first had matching pennies, I was like, all right, we only have, I don't like how this, I'm gonna draw it how I was drawing these boxes earlier. Because we had one box and we had two vertical lines, not vertical, two lines going through them. All right. The first time that we had matching pennies, it was like 1, -1, -1, 1, -1, 1, 1, -1, right? And later I switched up the matching pennies on you and kind of changed all the payoffs, right? So here we know that there's some sort of general form for matching pennies. So we kind of already knew that this game could be generalized because I already described it in some sort of more generalized form, right? So now it's up for us to figure out what exactly makes matching pennies matching pennies. How would we generalize matching pennies? All right. Anybody have any thoughts about matching pennies?
You want to be player 2.
Not necessarily. In this first game, you're kind of indifferent about being player 1 or player 2, right? In this game, it was better to be player 2. However, in this game, it didn't matter if you're player 1 or player 2. Both players would come out equally in this game, right? So it's not always better to be player 2. That's not something that's like necessarily matching pennies.
I don't think it really matters what you pick.
What do you mean?
I mean, like it's 1, 1, 1, 1, 1, 1, 1, 1. There's one side you gain something, there's one side you lose something, there's one side you gain something, and one side you lose something. Which is basically
that's actually that's one of the properties of matching pennies. So one side you win something, one side you lose something, one side you win something, one side you lose something, right? That's one of the properties of matching pennies. Right? The goal of matching pennies is that as player 1, you're trying to match heads of heads and tails with tails, and their goal is to do the opposite, which is match your tails with their heads and your heads with their tails, right? You're trying to do the opposite. So another big thing about matching pennies is how it is a zero-sum game, right? If you remember, I just said stuff about zero-sum games when we were covering this the first time. And that is whenever you gain money, the other person loses the equal amount of money, right? Whenever you lose money, the other person gains that amount of money, right? You gonna say something?
Basically, everything's the same. Like, for example,
in these
3, 6, 6, 100, 100.
Yeah, in these sort of boxes, we have to have some sort of positive number and then some sort of negative number, and that's the same exact number, except it's negative, right? That was one of the core characteristics of matching pennies. And actually what we just did there is we actually just described all of the core characteristics of matching pennies.
2 years of jail if you get it wrong. And 2 years of luxury if you don't. 2 years of good luxury if you get it right.
I mean, we never exactly told what exactly these numbers represent, right? Okay, so actually when we generalize matching pennies, we get some sort of matrix that looks like this, right? Whenever you actually get matching, you get an A amount and your other person loses A amount, right? This is sort of the something is positive, the other thing has to be negative, right? And we see that in all the squares. Something is positive, something is the equal number but negative. Meanwhile, the opponent's goal is to not match the pennies. Therefore, they gain whenever they are different. So heads, tails, those are different. Therefore, they gain whenever they are different. Heads, tails, they gain when they are different. You gain when they are the same, right? So this is actually a generalized form of matching pennies. And we can do something similar to how we solved, We can do something similar to how we solved the Stag Hunt game.
So what you do is go random, so no one can predict what you do.
Yeah, we already figured out that we need to do random whenever we did the mixed strategies game, right? The mixed strategies lecture. Remember that?
Yeah.
We already figured out that we need to go random, but here we've generalized exactly how random we need to be, or exactly what probabilities we need to pick each of these with. Basically, if you plug in all of the numbers into this equation, the expected value that we get from heads and expected value we get from tails, after doing all of the mathematical simplification, we get the probability that that player one should choose heads.
Did you use Google for that?
No, I did not actually. I calculated that all by hand, but it wasn't very hard to do by hand because it wasn't that bad to do by hand if you know what you're doing.
And then you accidentally get the question wrong.
No, this one is checked. I checked it to make sure it was right. I checked it with something I calculated myself as well. So maybe it's something I calculated myself was wrong as well.
You calculated a calculator.
Yeah, in a way, this is sort of like calculating the probabilities beforehand, right? Because now, no matter what sort of matching pennies game, like you're the other player, somebody you're playing against, or I don't know, your friend offers to play this matching pennies game, and you know exactly what the best strategy is before,
Best strategy is to go random.
Well, it is to go random, but with what probability? And that probability we just determined is B plus D over A plus B plus C plus D, which is kind of a pretty nice formula, but also kind of mean at the same time. But it's as nice as we can get. So player one has a probability of B plus C divided by A plus B plus C plus D. That's what they should pick heads with the probability of. Meanwhile, we can also do something similar with player two. And that's exactly what's on the side. If you want to go through the math, you can just like look at my slides after class or something. I don't know. The math here is correct. I made sure it was correct. But yeah, essentially we know
ask us what's the to this problem. Look back in the slides and tell you yourself the answer. Yeah, that's correct.
Yeah, let me pat myself in the back for checking my answer with myself. Yep. All right.
You check your answer with your own answer and you probably got it wrong again.
So, you remember how 2 weeks ago we spent all of that time figuring out how to play matching pennies in this sort of case, right? We spent a lot of time figuring exactly how to figure this out. Well, now we have a formula to do it for us. So we can check to make sure our formulas are right, to make sure that they were the probabilities that we got. So these two numbers were the probabilities that we got 2 weeks ago. If you can remember that far back, it's like pretty far back. So, all right. So we said the probability that player one should choose heads was 6 over 11. So let's like plug in the numbers to see if we get that. So from this sort of matrix, we see that A is equal to 2, B is equal to 5, C is equal to 3, and D is equal to 1, right? Therefore, if we have B plus D divided by A plus B plus C plus D, we get B plus D, that is 5 plus 1, which is 6, and we divide that by 2 plus 5, which is 7. 7 plus 3 is 11. 10. 10 plus 1 is 11. Therefore, our probability is correct, and our equation then is probably correct, right? If this equation works here, it's probably working. All right, we can test it with the other player, right? We said that player 2 should have a probability of 4 over 11 of choosing heads. And if we check this, we see that we have 3 plus 1, which is 4, and we add them all up. We already did that in the last one, or 11, 4 over 11, and this works, right? Also, with this question, I introduced the concept of the expected outcome, or the expected payoff, right? So you might be wondering if we can find a general form for the expected payoff. And you're right, we can do that. Except, you'll see on the next.
How do we know that we said yes?
What?
How do you know we said yes?
Do you mean said yes?
Said, oh yes, you're correct. I guess.
I don't remember what I said 3 seconds ago. I'm sorry.
Okay.
Okay. We can do more math. Yeah.
More math.
We can do more math to figure out exactly how to get the expected outcome, right? We said the expected outcome was the probability of us getting H times the payoff of getting HH, probability of getting HT times the payoff of getting HT, the probability of getting TH times the payoff of getting TH, and finally TT. So
Is there going to be more math?
I didn't even do the math. This math is so bad that I didn't want to do it. So here was the start of doing the math, but I don't know, if you want brownie points, and you can evaluate all of this junk. I didn't evaluate it. So you can find, in general, if it's worth it for you to play. However, it's very painful to figure out. What?
Use Google. And then get brownie points. Say you did it by hand.
I don't think Google can even simplify this down. Also, because Google is Google. There's also a whole bunch of stuff I'm missing here. You'd have to add in, what is this? More math stuff to this to make this valuable. You have to double this thing's size, which is kind of crazy. This equation is already kind of ridiculously long. But if you want to evaluate it for fun, I don't know. Again, you can do it if you want.
Yikers.
Exactly. Yikers. Yikers, dude. Okay. Moving on. If you want to figure that out, then be my guest, but I'm not going to do it. I might do it after the lecture, but I'm not going to do it right now.
Probably take
okay, we're going to cover the hobbies game in a little bit. However, I want to introduce the third round.
The homework again.
Yeah, the homework, the third round of this. So I'm going to just put that in chat. So everybody picks a number from 1 to 100, and the person who's closest to 2/3 the average wins. And I actually have all of the responses recorded on this sheet right here, which is where I've been keeping track of how the rounds have been going. So if you want to look at the averages, you can see the averages to the previous games right here and use that to predict how it's going to go, right?
What?
So the first time we played, the average was 33, 2/3 the average was 22, and our winner said 21. Second time we played, the average was 21.4, 2/3 the average was 14.2667, and our winner said 14. Also, I'm pretty sure you can enter in decimal places. So if you want to enter in decimal places, you can try like 12.2, because that was the winning guess last time.
What's 2/3 of 12?
I don't know. Maybe you could use Google to figure that out. Actually, I'll tell you right now, it's 8. So if you want to say 8, you can say 8. It's cool.
It's cool.
You know, based on these previous results, I would.
Submit a decimal.
You should be allowed to submit a decimal, I think.
Okay.
Anyways, I'm not going to go over who wins this. I'm going to go over who wins this next time in class. So in the meantime, I'm going to go over this game, which is, I don't know, a new game.
Movies and shopping.
Yeah. So
what is this for?
So essentially, it's you and some friend of yours are deciding where to go, and you prefer to go to the movies. However, the other person wants to go shopping, right? So you want to go to the movies. The other person wants to go shopping. What do you do? So
Go to the movies.
Yeah, but then what if the other person wants to go shopping? So they go shopping. So you guys.
So you get 0-0.
You guys.
Then you get to go where you want to go, and then they get to go where they want to go. It's simple.
However, because of the rules of this game, you guys would prefer to go together, whether you're going to the movies or shopping, which is sort of represented by what we have down here, right? If you guys do separate things, so if one person goes to the movies, other person goes shopping, then both of you guys have a bad time because you guys aren't like hanging out with each other. Similarly for movies and shopping right here. However, if you guys actually match, then let's say if you match movies, then because you prefer to go to the movies, you will get, you prefer to go to the movies, you get 2, while the other person gets 1. You can imagine these as imaginary enjoyment points, right? Trying to maximize your enjoyment points now. And if you guys both go shopping, then because you don't like shopping that much, you only get 1, which is worse than just 2 that you could have gotten from going to the movies. However, it's still better than going separate ways, right? If you go to the movies and they go shopping, then even though you're supposed to prefer the movies, you kind of have a rotten time, bad time, because the other person wasn't with you.
So don't play that game.
I mean, there's nothing to lose, right? Also, it's not like you decide whether you want to play this game, right? Like you could be out going for you're just out with your friend walking about. You're like choosing anything there, and you're just suddenly thrown into this decision, right? It's not like you can just decide not to play. I decide not to play life. Ha ha ha. Okay.
What's life? I don't have a life.
Sad is a very sad statement. But so we have this payoff matrix right here. So does anybody have any ideas what they would do?
I would go to the movies because the other person would use the logic that you would want to go to the movies.
But then the
problem with that is that the other person will use that same logic, so they will go shopping because they think that you're going to go to shopping too, just because of the.
Wow.
It's very confusing and I can't explain it well.
Yeah, I mean, it's kind of like, what is it? Kind of like matching pennies in a way, right? Except both players want to match, and they're still trying to figure out how to match.
Just basically, if you go shopping, then they'll go to the movies because they'll think that you're going to go to the movies.
So, in fact, we can actually solve this by, what is it? Like randomly deciding where we want to go to the movies and shopping. Yeah, more algebra. So, essentially, if you do the math here, you can figure out that in this case, player 1 should pick movies 2/3 of the time and go shopping 1/3 of the time, and player 2 should go to the movies 1/3 of the time and shopping 2/3 of the time. And that's a mix. That's an equilibrium. However, the more fun thing to do here is to generalize this. So here, instead of instead of movies and shopping, we have going to a ballet and going to watch a fight. However, it's still basically the same game, and we can generalize this using this sort of box here. So A is greater than B is greater than C, and you can actually do the math here to figure out that the probability of that overall, after you generalize it, that you should choose ballet is B minus C all divided by A plus B plus 2C. which is kind of a fun equation to get. Anyways, that should be the last slide. That's checking. That should be basically the last slide. Wow, I actually got everything done in time.